last video, you learned about how to write equilibrium expressions. In this video, I'm going to show you how we can actually calculate K, and at the end, how we can interpret what K actually means. So I've got two problems for you. Let's get started. The following equilibrium concentrations were observed for the Haber process at 127 degrees Celsius. The Haber process is, and here it is right here, calculate K. So in order to calculate K, the first thing we have to do is write an equilibrium expression. Each reaction has its own equilibrium expression. So it's going to be K EQ equals the products over the reactants. Turn your coefficients into exponents. So it's going to be NH3 squared. There's our product. We checked all the states of matter first. All three are gases, because remember you have to cross off solids and liquids, divided by N2, the concentration of N2, times the concentration of H2, and we turn the coefficient into an exponent, cubed. Now, we were given our concentration values. It is really just a plug and chug now. We've got NH3 is 2, so it's going to be 2 squared divided by N2 is 1, and H2 is 2, cubed. And I want to make sure I write all my digits in there so I can check sig figs at the end. So 2 squared is 4, and 2 cubed is 8. So when we divide those, we get 0.50. There's your answer. Now some of you might be thinking, what is the unit for K? It's a good question. First of all, chemists don't write units for K. So do not write a unit. Now if you do, each reaction actually has its own unique unit. It depends on the equilibrium expression. It depends on the reaction. So in this case, each of these is molar, so it'd be molar squared, divided by molar cubed. So this would actually be molar to the -2. That would be the unit for this one. I am not going to make you figure that out each time. It is a waste of time, and most chemists don't ever write units for the equilibrium expression, so you definitely don't either. So if you do end up putting molar here, it's wrong. If you do desperately want a unit, you need to make sure it's correct, and most chemists would look at you like you're weird if you included it. So let's talk about what this number actually means. It is less than 1. Do you see that? That means the bottom is bigger than the top. That means there are more reactants than products. Which side is favored then? Definitely the reactant side. That means the reverse reaction to produce the reactants is the favored reaction. Now, let's read this second problem. Now, I do want, before I move on, I guess I do want to talk about sig figs. 2, 2, 2. There should be 2 in our final answer. So do make sure you're still watching sig figs with this. A different experiment was performed using the same process and at the same temperature. Ooh. So we're doing the same temperature, but different concentrations. Do you remember? The only thing that will actually affect K is temperature. So if this problem works out, we should get K to be 0.50 or something very close. We should get the same answer because we have not changed the temperature, but different concentrations. Calculate K. So we're going to use the same formula, but now we're going to plug in new numbers. So the concentration for NH3 is 0.86, and we have got to square it, divided by concentration of N2, 0.75, times concentration of H2 cubed, 1.25 cubed. Now, this one's, I'm not as good at calculating in my head, so I'm going to grab my calculator. You can do the same while I'm plugging this in. 0.86 squared divided by 0.75 divided by 1.25 cubed. And ooh, this is so exciting. 2 sig figs yet again, because 2, 2, 3, our lowest number is 2. So we need to have 0.50. Woohoo! We got the same thing. Does that make sense? Yes, because we did not change the temperature. If we had changed the temperature, K would have changed. And that I will need to talk to you about when we start talking about Le Chatelier's principle. So here's how you do equilibrium expression calculations. I hope you enjoy them.